Welcome back, everybody. This is Lecture 5. Wouldn't that be annoying if I had to talk like that every day? It is funny. I caught you off guard, didn't I? Uh-oh. We're in trouble now. Katie's going. I sometimes do stats for the ESPN people that are on TV, and it's funny how they'll be talking to you, like this, and then the camera comes on. Oh, ladies and gentlemen. It's like, where'd that come from? Why don't you just talk like regular English? I need to learn names, so if you see me looking at my seating chart, looking at your face, bear with me till I learn names. If you go by a nickname that you didn't write on here because you felt like you had to write your formal name or given name, then let me know that, because I'm going to go by the name that you wrote down in class the first day. We have one method of approximating the area under a curve when we can't integrate it. We're going to try to wrap up the other method today and look at error estimates, and that should keep us kind of on schedule, on target for where we should be. We have the trapezoidal approximation. It should look something like this. This is in your book. You don't need to copy it, but the first one up here, we're going to try to integrate something that is not necessarily patterned, or we don't have a table readily available, and we want to use a trapezoidal approximation. If you see a capital T with a little subscripted number, then that's T4, T5. You can use any number here. That's the number of trapezoids that you're constructing. So it's delta x over 2 or h over 2. Remember, we factored out a 1/2 h. F of x0, 2f of x1, 2f of x2, and all the others have a coefficient 2 until you get to the last one. It's only in there once. So basically the first one and the last one are entered in here once. I don't know. Why is that true? How in the world could you remember something like that? Where'd the 2's come from?
Because you have two sides of them, like two trapezoids share one side.
Okay, there we go. These trapezoids, when you put them where one ends, the other one starts, that base, if you want to call it that, that side, is shared by two trapezoids. Therefore, it ends up in the formula twice. So it would have been 1, 2, 1, right, if we had one trapezoid, but that other base is shared, so it ends up being in there twice, and basically all of them end up in there twice except the first one, which is not shared, and the last one, which is also not shared. Delta x b minus a over n, we did that. X sub I don't know if I wrote this down exactly this way yesterday, but if we want x sub 0, we start with a and we add delta x in 0 times. X sub 1 is a plus 1 delta x. I think I wrote it this way instead. X sub 3 would be a plus 3 delta x's, and so on. So x sub I in general is a plus I delta x. We did look at an example. I think we used 1 over x, so we could check it. The area under 1 over x from 1 to 2 is exactly the natural log of 2, but an approximation of that was 0.693. I don't know if we went any further than that. 315 maybe. And then we got how many trapezoids did we do? 4 trapezoids. And we got close to that. I think we got 0.697. So we did either T4 or, I think I wrote it yesterday, trap 4. So we had 4 trapezoids, and we got the area under this curve, this area. The nice thing about this example is we can check it. We know what the exact answer is. With 4 trapezoids, I think we got 697. Does that sound right? And this is exactly the natural log of 2, which is approximately 0.693. So we did reasonable. We had an error in the 3rd decimal place. That's pretty good accuracy for just 4 trapezoids. So at this point, we want to jump to the other one. Where are we with respect to the other one? I think we left off with the fact that if we start at x0, I'm going to go ahead and have this arbitrary parabolic lid to this region, pick up x1, and then we'll, so basically the parabola that we're forcing to contain the top of this should be a little bit higher accuracy. You'll see that will kind of looks like the same, but it's actually two parabolic regions. We can be more accurate with two parabolic regions than we were with four trapezoids. So the accuracy is a lot better. By the way, there's a third method in the book. Just to point it out, in case you read the book and you say, I wonder if we need to know that, there is a midpoint rule, the bottom of page 412. It's kind of right in there at the level of the trapezoidal approximation. So I just chose one of the two, and I happen to choose trapezoid. So we're not going to do, I'm not going to ask you to be responsible for the midpoint rule, very similar to the trapezoid rule. And there's actually a reason why I chose the trapezoid rule, because I think it leads real nicely into Simpsons rule. So with this, now it looks like two regions. If you want to kind of compare and contrast with the trapezoidal approximation, it kind of is two regions. As far as determining h or delta x, so this is still h, and h will call our delta x, which is still going to be b minus a over n, but it's kind of halfway through the parabolic region. We're still going to call it h. I think we got to the point yesterday where we had the area with Simpsons rule, and it's approximately equal to the actual area under the curve. H over 3, I think we got to that point. Y0 was in this position, and we decided that Y0 was really f of x0. What was the coefficient of that middle one that we were trying to pick up that point where the dotted line is? That was a 4. I think we kind of ended class with that, right? That's where we left off. For h, you can plug in delta x, and we're still okay with that. Now, let's suppose that we want to throw in the next parabolic region. So I want my starting segment to be here. I want the point in the middle to be x3, and my end one to be x4. So I want the parabola, the arbitrary parabola, to capture those 3 points. So what's it going to look like? Let me move this further to the top. There's our first one. So our next one, we'll have an h over 3 out in front. My starting value was x sub 2. So shouldn't I have f of x2 plus 4 f of x3 plus f of x4? Does that seem to be the case for the next one? Here's the picture. So I want one of these, 4 of these, and 1 of these. So what happened at x2? Wasn't that line segment, or that distance, that f of x2, wasn't it in the first parabolic region and also the second? And won't that be the case if I continue? x4 will be in both of them. So what's going to happen when I try to group those things together? Well, I'll factor out the h over 3. I've got f of x0. Do you see another f of x0? That's the only one. I've got 4 f of x1. Do you see any other f of x1s? That's it. Now we start the overlap. Here's an f of x2, and here's another f of x2. So we've got 2 of them. Here's 4 f of x3. Do you see any other f of x3s? Now, here's an f of x4. Will there be another if I were to continue this with another parabolic region? There would be another f of x4. You don't have to write quite this many, but this is the first time we're writing it down, so I'm going to write enough to establish the pattern. F of x4, there'd be what? 4. F of x5, and let's go ahead and stop this thing at 3 parabolic regions. There'd just be 1, right? F of x6, is that right? So if we were to stop it at 3, so we see the pattern, we've got 1 f of x0, we've got 1 f of x6, and then the pattern is that we're alternating 4s and 2s, beginning with a 4 and ending with a 4 until we get to, we've exhausted the number of parabolic regions. So you could call this two different things. You could call it, well, you could call a lot of different things, but they wouldn't make sense. You could call it simp. In a sense, you kind of have 6 regions, but there are just 3 parabolic regions. There are 3 different times we had this 1, 4, 1 configuration. 1, 4, 1, 1, 4, 1. But it looks like on the picture, I'll dress this picture up just a little bit more. So there is x5, and there is x6. So there's our 3rd parabolic region, but it kind of, in a sense, you can say 1, 2, 3, 4, 5, 6 if you're going the number of times you move delta x from left to right. But 3 and I'll try to identify it as both. This would be either simp 6 or simp 3 parabolic regions. Now, if you use 6, you always have to have an even number. And the authors address that in the reading, and I do encourage you to read the material that's in the book. But you can have as many parabolic regions as you choose. It could be even or odd. But since each parabolic region includes 2 other regions, that's why it's always got to be even if you call it like simp 6 or simp 8 or simp 12. 12 would mean 6 parabolic regions. 10 would mean 5 parabolic regions. So it's all based on the top of the region being a parabola, even though we're capturing that point in the middle. So to summarize that one, before we look at an example, here's what Simpsons rule looks like. H, or delta x over 3. Now they call this S sub n. The way they refer to it, it would be, n would be an even number, and it'd be kind of the number of delta x's you're crawling along. F of x0, it's in here once. F of xn, which is whatever your last one is in here once. The next coefficient is 4. The next to last coefficient is 4. And you're alternating the 4s and 2s. So that's the reason why I choose to look at trapezoidal approximation, because it has this similar kind of sharing of sides that cause these to all be 2, and for us to alternate in 4s and 2s. It'd be nicer if it were 2s and 4s. That'd be 24, which is clearly the best show on television. Okay. So other than this class on 5 p.m. On every day, channel 18, second in the ratings, I'm certain, would be 24, which we just had 2 hours of premiere, and then the very next day we had 2 more hours. So it's just like heaven. Now we've got to wait another week to see another version of 24. All right, any questions about the formula? Any of you watch it? 24? Pretty good, isn't it? I won't tell you about any of the things about Jack Bauer and what he did and didn't do, but it's good.
It's like my favorite show.
Let's look at an example. So let's look at an answer that we know the exact answer, natural log 2, approximately 0.69315, I think. And we did 4 trapezoids, and we got 0.697. Let's just do 2 parabolic regions. So it kind of looks like the same diagram because our delta x will be the same. So we're going to come out here 1/4 of a unit. So our h is going to be 1/4, or delta x, b minus a over n. So it's 1/4. So it looks a lot like the kind of the trapezoid setup we had yesterday, but just basically 2 parabolic regions. So why am I calling it a parabolic region? Where'd that come from? Just made up a name? Histographic. Maybe it's a histographic region. Just a name I just made up. Does it work? Histograms, remember those? I'm stretching it there. I just came up with another word.
2 parabolic regions, how did you get n to be 4?
Because there are 4 kind of stopping places along the way. When I call this a parabolic region, and by the way, what's the answer to that question? Why is it a parabolic region?
You're making a parabola.
Because the top is a parabola, right? So we're forcing this parabola to grab all 3 of those points. So the fact that we're forcing it to grab this point in the middle, we're establishing this as kind of a subregion, or it's a part of the parabolic region, but that's still classified as h, because we wanted the area under this curve. And I know we did this kind of quickly, but we went from x0 to x0 plus 2h. So by the time we started here and ended here, which is the other side of the parabolic region, we had moved over 2h. So that means the middle point is over h. So that's where this kind of formula came from. Chandler?
Does it make it more accurate by doing that, like to make it a parabola? Now, if you didn't have that middle, wouldn't it technically be...
Well, there's a whole bunch of parabolas that could capture this point and this point.
Yeah.
But the fact that you force it to go through here, that
Guarantees.
kind of makes it stay closer to the curve. Okay, did I answer your question all right, Nicole?
Yeah.
Okay.
Thank you.
So let's go ahead with just 2 parabolic regions, seemingly less accurate potentially than 4 trapezoids, but it's going to be actually a whole lot more accurate. So this area, so it's okay to call it 4 because there are, in a sense, kind of 4 regions. Or you could refer to it as just 2 parabolic regions. So we want, tell me what to write down here. How do we start with Simpsons rule?
1/4 over 3.
That's right. So 1/4 over 3. So it's h over 3, or delta x over 3.
Times f of 1 plus 4f of 1.25.
Okay, I'm going to call it 5/4.
Plus 2f of 1/2. Plus 4f of 1.75. Plus f of 2.
Once again, proof that I'm not needed. Okay, I'm just kind of here to write stuff down that you tell me. Everybody go along with that. So you always have a quick visual check. Is the first entry and the last entry, do we have one of those? Yes. The second entry and the next to last entry, do we have 4 of those? And then are we alternating 4s and 2s? We are. So f of 1, what is our function that we're trying to approximate the area under? 1 over x, so it'd be 1 over 1. 4 of these. What's 1 over 5/4? 4/5. F of 3/2, what's 1/3/2? 2/3. Kind of some similar numbers that we had yesterday with trapezoid, but different coefficients. 1/7/4, 4/7, and the last one's in here once. F of 2 is 1/2. So there's our arithmetic. It's supposed to get us a reasonable approximation, and I think we'll find that actually the accuracy is a whole lot better with Simpson's rule. And we'll talk about errors associated with them, and you'll see just by how the error is written out that it is going to be a whole lot more accurate. Let's just go one step further. What do we have here? 16/5 plus 4/3. It is an approximation, so let's use our calculator to take it from here. 3. Okay? A lot better accuracy. I think the other one is 0.69315 if you did natural log of 2. Somebody check that. Just punch in natural log 2. 0.69315. Okay. So we're at 693, so we've got accuracy to this column, and so our first error is in the 4th decimal place. Quite a bit better, actually, than we got with TRAP 4, because we got 0.697. Not awful, but this is a whole lot better. Any question about the kind of the arithmetic or the format of how we use that approximation? This is called numerical integration. Did any integration take place? No. We didn't integrate anything. It's kind of imitating that in the sense that we're getting to the same answer, but we did not integrate. We're doing it all numerically. There's a great example in your book. I urge you to read this one. I do want to point out a couple things about it. It's at the bottom of page 418. It's got a real kind of edgy curve, and what this curve is D of t is the data throughput measured in megabits per second. Use Simpson's rule to establish the total amount of data. So here we've got a rate at which data is being transmitted, megabits per second. So it's a rate. So if we anti-differentiate this rate, what is a rate? Isn't it a first derivative? It's the rate of change of something. So we're anti-differentiating, kind of. We're imitating an antiderivative. What would you expect the area under this curve, which is megabits per second, to be? Megabits, right? So you can, if you have some data, we don't have a function, we just have data points. There's a table, by the way, on page 419, so we don't have to actually try to read the chart, read the graph. So you can do the same process if you don't even have a curve, you just have a table of data. And if the curve itself is a rate of change, then you're going to find whatever that is the rate of change of, you're going to find that amount by finding the area under that curve. So that is done, so you probably ought to take at least a brief look to see that they're doing the same thing. They've got 4 of the second entry, 2 of the next one, 4 of the next one, and so on in their work here. So it is megabits per second. Area under that curve is megabits, and they still use Simpson's rule. No function is known. We don't need it. We just have a table of data. The bottom of 419, and where's the other one? On page 415, and I'm not going to ask you to memorize these, but I do want to take a brief look at them today in class. Actually, yeah, this is as good a time as any to do that. The error bounds or the error estimates associated with these. So you can look at the error associated with Simpsons rule and that associated with trapezoidal rule. So here are the error bounds. So we want to pay attention to the one that we looked at, which is trapezoidal. This is the midpoint rule, which we're not examining in this class. So here's the error associated with trapezoidal approximation, this type of numerical integration. Where this comes from is actually in another math course. It's in a math course, probably the first time you would actually derive this is in Math 425, which we're not there, obviously. We're in 241. This can be derived. It's not, something that's absolutely ridiculous to get there, but that's not part of what we're doing in this class. So we'll take what's handed to us, and then we'll try to examine it and see why the error associated with trapezoidal approximation is larger than the error associated with Simpsons rule approximation. So the error absolute value, so we don't know if we have too much or too little. So it's just how far away from the answer are we going to be? What's the absolute value? This k, we need to examine what the k is. But setting that aside temporarily, we would take the values that have been given to us in the problem, b minus a, that quantity cubed, over 12 n squared, where n is the number of sub-regions that we have in our interval. By the way, I think I explained why I chose the trapezoidal rule. If you compare the error associated with the midpoint to the error associated with the trapezoidal approximation, which do you think is better?
Midpoint.
B minus a cubed, we've got it over here.
Yeah.
N squared, we've got it over here. This has a 12 and this has a 24. Ooh, 24. That's the best show on television. I knew it'd get integrated here somehow today. If you have a larger denominator, doesn't that mean your error is smaller? So midpoint actually does a little bit better, right? The error would be half as much as trapezoid, but I did have a reason for examining trapezoid so that it would kind of lead us a little better into Simpsons rule. Now, what is this k? K is the maximum value of the second derivative over this interval from a to b. So if you find the second derivative of the function, by the way, this is going to be really difficult to do when you don't have a function, right? You just have a data set, then we're going to be out of luck with the error bounds. But the maximum value of the second derivative over the interval, and we'll do an example problem to figure out what these would be for the two examples that we've chosen to do thus far. So let's see what that looks like. Let's see what that looks like before we examine the error bound for Simpsons rule. So we did a problem. We approximated this. Time permitting, I'd like for us to do another problem that is a little bit more complicated than 1 over x. So you can see that, this is a good first example, but it's a little too simplistic, possibly. So our A is 1, our B is 2, and we did 4 trapezoids, so N was 4. So the error for us I'll leave out the K value right now. We'll come back to that. B minus A. That doesn't really get all exciting, does it? 2 minus 1 cubed over 12 times n is 4 squared. Now let's look at this k value that's going to occupy this position. We need the second derivative, so our original f of x is 1 over x. First derivative is what? No, that'd be going the other way. We want to derive, that'd be integrating. Negative 1 over x squared. So it'd be negative 1 x to the negative second. Good. Positive 2 x to the negative third, or 2 over x cubed. So we want to maximize that on the interval in question. What's the maximum value of the second derivative? Notice where x is. X is in the denominator, so if we want to make this fraction as large as possible, we want to make the denominator as small as possible, right? Not as large as possible. So that's going to happen at 1, right? So this k value that we're looking to insert here, the maximum value of the second derivative over this interval is 2 over 1 cubed, or 2 over 1, or 2, right? So there's what kind of error we should expect with the function that we had, 1 over x, and the limits that we had from 1 to 2, and the number of trapezoids that we had, which was 4. So let's see what that is. Numerator is what? 2. Denominator is 1 over 96. Somebody give me a decimal for 1 over 96.
0.01.
0, 1, 0, 4.
Yeah.
Now that's the maximum error that we're going to have. Now we actually found the error to be in what decimal place? We got the 0.6 good, the next one was a 3, and that was good, right? And then we found an error in the next column. So we actually found the error to be smaller than this. This is the maximum. This is the error bound. It's the most error we're going to have. So it says, at the most, when we do this process with this function over this interval with this number of trapezoids, that's the largest our error could be. So that's not too bad. We actually found it to be smaller than that. Questions on this? This is probably not a test question. Okay? I'm not going to ask you to evaluate the error bound. There is another way to use error bound that I think is more helpful than this. If you want a certain level of accuracy, how do you use this fact to decide how many subintervals you want to get that desired level of accuracy? That's a more valid problem, but this is almost kind of after the fact. All right, error bound associated with Simpsons rule. Now let's kind of compare and contrast things that we see down here with things that we saw up here with the error estimate associated with trapezoidal approximation. We've got a k. We'll examine that in a minute. It's different than the k was up here. B minus a to the fifth as opposed to b minus a cubed may or may not have an impact, but it's in the numerator. Doesn't have an impact on this problem, right? Because b minus a is 2 minus 1, which is 1. No difference between 1 cubed and 1 to the fifth. Now let's examine the denominator. Now you start seeing some differences. Where there was a 12, you see a 180. That's a big difference. That says already it's going to be a whole lot more accurate. And where there's an n squared, now we've got an n to the fourth. So if n is 4, instead of having 4 squared or 16 down there, we're going to have a 4 to the fourth, which is 256. Is that right? I think that's right. So our denominator is a whole lot bigger, which means that the error is smaller. We did a whole lot better with the approximation with Simpsons rule than we're going to be able to do with trapezoidal, or if we chose to do so, midpoint approximation. Now, what is the k value? This k value, I don't even know what that means. What's that notation? Fourth derivative, right? Actually, I do know what it means. I was kind of seeing just to see if you knew what it was. When you see a superscripted 4, it means we're tired of making all the little tick marks, right? Let's put a superscripted number up there. So that's the fourth derivative of the function is smaller than k. So we want this to be the maximum value I'll go ahead and put them here. Maximum value of the fourth derivative on our interval from a to b. This is a whole lot more accurate. Simpsons rule is a whole lot more accurate than either trapezoidal or midpoint approximation. So let's see what our choice, what kind of error. So we'll leave out the k value right now. B minus a to the fifth, 180 n. Now the n they're talking about here is the even number of kind of stopping places that we go along the way. This is not the number of parabolic regions. So n is still 4 for the problem we did. Now what about the k that occupies this position? So we got this far, last problem. I think that'll work. 24, we would expect the next one to be negative, right? So we're going to alternate in sign, SIGN, as we go. 24 over x to the fifth. Does that work? So the one we're skipping here is what? Negative 6. So we want to maximize that on our interval from 1 to 2. Again, x is in the denominator. We're going to maximize the value of that fraction by making the denominator as small as possible as opposed to as large as possible. So what do we want? 1, right? Here's another reason why this is a good first example. Can you imagine if this is, let's say the function is x times the cosine of x, and we've got to work our way to the fourth derivative? We may not have enough class time to do that, so we're trying to actually look at examples that would fit in the class period. So there's our k value. So what do we get for the numerator? 24? Gosh, that just kind of keeps coming up, doesn't it? 24, best show on TV. Other than this 241 broadcast. 4 to the fourth. 16 times 16, 256. Check me on that. So what do we get out of that? So what is that error, the maximum error approximately for this problem? So our error would be less than or equal to, what is this as a decimal? 5? Now, we actually did the approximation. We got 0.6933. Is that right? Don't tell Nicole what we were, don't tell her what we discussed there because that's kind of a secret. Sorry, just, you missed it. Sorry. Isn't that where we decided our error was, right? The fourth decimal place? And in fact, it may not even be that large because I think the calculator version for the natural log of 2 is 0.69315, and we had 0.6933, so this is the error at its maximum. We didn't find it to be this much. If this turned out to be the exact error, if this is crossing your mind, wouldn't we always be able to find the exact value by taking our approximation and either adding or subtracting our exact error? It's not exact error. It's kind of the worst that your error could be. So it's just to give you a general idea. We think we've got a pretty good answer. How good is it? How reliable is it? This is what's going to tell us that. So it's a error bound. It is not the error itself. This is probably a mistake, but if you have your book and you'll look at page 421, you'll see, starting with problem 7, 7 through 16 are some problems that say use trapezoidal rule, the midpoint rule, and Simpsons rule. Let's pick a method, not all of them, and let's pick a problem in there. That's where I'm probably making a mistake. One that looks a little worse than 1 over x, that was pretty tame for our first example, but maybe not the most hideous one in the list. 10, okay.
It's at page 420.
421,
421.
problems 7 through 16. So if you want more practice on this, because what you see in WebAssign is quite enough, and sometimes that's the case in this class, then pick an odd-numbered problem in here and pick either trapezoidal rule or Simpsons rule, do the problem, and see if you match the answer that's in the back of the book. So 10 was suggested. 0 to 3. That's considerably worse, but it's not the worst of those problems in this set. And they say n equals 6. Let's go ahead and use that. I don't care. Trapezoidal, Simpsons rule. And by the way, I give you that choice on the test. I will say, you choose trapezoidal or Simpsons rule. You do either approximation. Which do you want to do right now? Simpsons, okay. So this Simpsons rule with 6 regions is really just 3 parabolic regions. But we've got kind of these 6 stopping places along the way. We don't need a diagram. We kind of, on our first example, we paired that with a diagram, and I think that served its purpose. I don't know, does anybody see another way to do this problem? Does anybody see a way that we could actually integrate this? Possibly partial fractions. If this were to factor, is t to the 4th plus t squared plus 1. Is that going to factor?
You take a t out of the 2, and you can split the thing into t squared plus 1, and no, you can't. Never mind.
That's good. I mean, those are things that you ought to think about when you're looking at a problem, and then you go through that same thing. I don't know how many times I do that when I try to kind of mentally go through a problem. Yeah, maybe that, maybe that. No, it's not going to work. Okay? What did I just waste? 4 seconds? Okay? So you're not going to waste like tons of time by saying, let's try this, let me think about this. No, it's not going to work. I don't think we're going to factor that. If it were to factor, then that would be a good recommendation, because we'd have probably 2 irreducible quadratics. We could decompose into partial fractions and go from there. But I don't think we're going to have that luxury. This may be the only way to do this problem, as is the case with probably every one of those in 7 through 16 in that problem set. This may be the only way to do the problems, is to approximate. Get me started here. Delta x is 1/2 b minus a over n, which is 1/2. So our area with this level of approximating either 6 kind of stopping places or 3 parabolic regions It's going to be 1/2 over 3. Let's just write the kind of the functional notation now, and then we'll clean it up. F of 0.
2f of 1, 4f of 3 halves, 2f of 2, 4f of 2.5.
2.5.
Yeah, and f of 3.
Nicole is our designated Simpsons rule gal, and we will tell you what we discussed when you were out of the classroom because you reinstated yourself with that. Okay, we good with that? 0 is the first one, 3 is the last one. Next one is 4, next to last one is 4. All the others are 4s and 2s alternating. Think we're good with that? So 1/2 divided by 3 is the same thing as 1/2 times 1/3. F of 0 is just 1, right? Put a 0 in there for t. For f of 1/2. So isn't that going to be 1 over 1/2 squared plus 1/2 to the 4th? Is that delightful looking? Is that right? Not delightful looking, but it's kind of, we're stuck with that, unfortunately. 2, f of 1, that should be a little bit easier. What's f of 1? 1/3?
Yeah.
Right? 1 plus 1 squared plus 1 to the 4th. Now we go back to the bad ones. 1 over 1 plus 3 halves squared plus 3 halves to the 4th. F of 2, what's f of 2? One over 21. Got a consensus there on that. What do we need here? 4. I'm going to write that down here. F of 5 halves. Who picked this example? Who was that? No, I mean, they're all about the same. And f of 3 is in there once. 3 to the 4th is 81. 3 squared is 9, so that's 90, 91. Does that work? So I would fire up the calculator. It is an approximation, so let's let the calculator do the so-called ugly work as long as we know we're gathering the right things along the way. And we should have a reasonable, probably a pretty good approximation based on that error bound that we looked at earlier for this. I will do this one. You do this one before next class, and we'll see what we come up with, and then I'll also do the error bound to see if we're kind of within that ballpark. So this should finish us with 5.9. So we'll kind of tie up a couple loose ends at the beginning of class tomorrow and forge ahead into 5.10. Appreciate your attention.